Now we're going to look at how to use your calculator to find the same values we just found using the standard normal table. And you might think, well, which one should we use? Honestly, I don't care. You can use either one. If you prefer the table, you can use the table. If you prefer the calculator, you can use your calculator. Or you can use a mix of both depending on the situation. It really doesn't matter. However, whichever method you use, this sketch and this notation for your answer is the same. You would show the same work either way. You're going to show the same work. It's just the actual finding this number is going to be different. So on your calculator, just to write this down for reference, you're going to go to Menu 652 or Menu 653 for these problems. Okay, so we'll do this together on your calculator and you'll see what that means. I'm double checking. Yeah, that's correct. Okay, so the first problem, we're trying to find the probability of z being less than 0.54. So on your calculator, just clear this off, and we're going to go to Menu, Statistics, Distributions, and then Normal CDF, which stands for Normal Cumulative Density Function. Cumulative means that we're looking at an area under the curve between two values. Normal PDF is looking at an area, we're looking at the height of the curve at a specific value. That's useful for graphing, but it is not useful for finding probabilities because the probability is always an area under the curve, so it has to always be between two values. So normal CDF, you need to have a lower bound and an upper bound, and then mu and sigma. Mu and sigma by default are 0 and 1. So by default, we're using the standard normal model. So we have to think here when we go back. I'm going to leave this hanging for a second and go back and look at the picture. What is the left bound of this area? Well, the right bound of this shaded area is 0.54. Well, the left bound, this value continues on. If you look at this as a function, this is your x-axis here. And this continues, and it's an asymptote, so it never actually reaches an end. So our left bound here is negative infinity to 0.54. If we were looking to the right, it would be 0.54 to positive infinity. Okay, so we're going to leave the negative infinity, the upper bound 0.54, 0 and 1 are our mean and standard deviation. We push OK, and we get 0.7054, the same value that we got using the standard normal table. So I'm just going to grab this and copy so you can, and put this in our notes here so you can see what this looks like. Now, I want to stress to you that normal CDF is perfectly fine to write down on your paper as to show me what you've done, and actually I would encourage you to do so, but that does not count as showing work. Okay, the work that must be shown is the sketch and the probability statement. So this is the work to show, is all of this stuff. This is known as calculator talk. And calculator talk doesn't count as showing work. And the reason why that is because people who are grading the AP Stats test may or may not use the same calculator that we're using, and they may or may not recognize what this means. So you can't just use calculator talk to show work, but this drawing with this notation is commonly used by all statisticians, so this counts as showing work. Okay, so let's do another one. In this case now, we're looking at our left bound is going to be the negative 1.12, and the right bound then is going to be positive infinity. So when we do this here, Menu 652, only now this is negative 1.12. Now where do you get the infinity symbol? If you go down to your pi button right down here, and then over to the 2 to the right, there's your infinity symbol. Okay, 0.8686, the same thing we had before. Okay. So let's write that on here just to have as reference. So normal CDF, negative 1.12, positive infinity, 0, 1, equals 0.8686. Now this was the one where the table ran out of space. It didn't show what the value was, and we had to kind of estimate. We knew that it was less than 0.0002, so very small, but we really don't know exactly what it is. So if we use normal CDF here, normal CDF, we're going to be going from 3.89 to infinity, 0.1. And let's see what that calculator gives us. And I'm going to just go up here and just edit this one since it's very similar. Let's just change this now to 3.89. Or you can go through the whole menu thing and do it again. 0.99995, which is 0.00005. Wait a second, did I go for the wrong? I went the wrong way. Never mind, my mistake. That was wrong. I want to go the other direction. So let me just go into the menu here. Stats, distribution, normal CDF. The lower bound is supposed to be 3.89 and the upper bound is supposed to be infinity. I should have edited the other one. So I knew that didn't look right. So 0.00005, which is less than 0.0002. But this gives us a more exact value now. So 0.00005, which is 0.005%. Okay, very much smaller, a little bit smaller number. So now, does it matter which one I use? No. This is such a small number that it's, for all intents and purposes, practically a zero probability. So it doesn't matter which one of these you would report. If you want to say from the table or using my calculator, that would be helpful. Okay, now when we get to the ones that are in between two numbers, this is where I think you'll find the calculator preferable, because you don't have to look up two numbers and subtract them. You can do it all in one step. Because when we use our left bound now, our left bound is just going to be 0.49 and our right bound is 1.82, and then our mu and our sigma. So we do this all in one step. So menu 652, and my left bound is 0.49, my right bound is 1.82, and all in one step 0.27777. Okay, you can round it to 4 decimal places is fine here. 0.2777 rounded. Okay. And then same thing here. I can do the same thing with negative 1.5 and positive 1.5. So this one I am going to copy and paste because I can just do this, and let's just kind of back all this up. It's totally up to you whether you copy and paste or just do the program over again. It doesn't matter to me. Comma 1.5, comma, and there's our 0.8664. So we're getting, you can see we're getting the same numbers that we get either way. And so I'm going to let you decide when it's easier to use one or the other. Okay, now this is one where it will definitely be easier to use the calculator. This is the one now where we're going to use menu 653. This is called the inverse norm. In the inverse norm function, we start by putting the area in decimal form. We have to use decimal form for this. And then mu and sigma. Okay, so we're going to put in 0.85, and I should be more specific here. It has to be, I'm going to erase this, sorry again. This is the area to the left of the boundary. Okay, it's the area to the left of the boundary. So if I said, so when we're talking about 80th percentiles, then obviously it is going to be to the left. But sometimes I might ask, what's the boundary line for the upper 10% or something like that? And then in that case I would want to put 90% in there, because if it's the upper 10%, then it would be 90% below. So let's go and look on the calculator and then we'll add it on to here. So we're going to go to Menu, 6, 5, 3, inverse normal. And inverse normal asks for the area, so I put in 0.85, and then I have the 0 and the 1, and okay, and notice 1.036. Now remember we said 1.04 was closest, but it was in between 1.03 and 1.04. So now we know exactly what that value would be in between. Now you might think, well, exact is better, right? Well, exact is good, but remember in statistics, exact isn't exact. It's always an approximation, because for one thing, this normal model is going to be an approximation for a set of data, so it's not going to be exact anyway. So whether you say 1.04 or 1.036 is not really a big deal, to be honest. Okay. Now if we look at this one, same thing, only instead of 0.85 we're going to have inverse norm 0.2501, and we should see something close to negative 0.675. Remember we sort of estimated that it was about halfway between, so it should be pretty close to that. So I'm just going to go up here and change this to 0.25. Negative 0.67449, so that's pretty darn close to 0.675, not bad at all. So I'm going to grab that. I like to copy and paste when I can. Control copy, and here we go. Okay, so now you have a good idea of how to use the inverse normal function and normal CDF, as well as the table, to find areas under the standard normal curve or z-values corresponding to certain areas.